all real numbers, right? We can go from negative infinity to positive infinity. But what we have to do is you can pick any value c that's in between here as long as it's continuous, and you can split the integral up along that point c. And usually there's a convenient value of c to pick based on what's inside the integral. So once you've split it up, you'll then use guideline 2 to solve this integral and guideline 3 to solve this integral. If the answer to the limit is a real number, then we say that the integral converges. If the limit does not exist, right, and or the limit is infinity, we say that it diverges, right? So for these two guys, that's really easy. You're just doing one limit. But for these, if this converges and this diverges, then the whole thing diverges. So they have to both converge in this case to get a convergent limit here. So for some of you that might be wondering, when the hell would you ever do this? All right. Well, if you look at just a normal curve in statistics, right, these tails go all the way from negative infinity to positive infinity. So in stats, we actually do double improper integrals all the time because we know the total area under the curve is supposed to be 1. So in statistics, what will happen is we'll set this up. We know the answer is 1, but we may not know some things inside the integral, and by knowing the result is supposed to be 1, we can back solve for constants and figure out maybe what the curve actually is, what the function is. So it's actually a very, very, very useful thing. I did those in grad school like all the time. So let's look at some really basic improper integrals so you can kind of get this technique down. So the first one I want to look at is the integral from 1 to infinity of dx over x. So the first thing we say is, well, we have to change the bounds because you are not allowed to plug infinity into things. So we say, well, this is the limit as b goes to positive infinity of the integral from 1 to b of 1 over x dx. So the first thing we want to do is we want to complete the integral. So the antiderivative of 1 over x is natural log of x. So that means I'm taking the limit as b goes to infinity of the natural log of x from 1 to b. So then we plug in our bounds, and we'll get the natural log of b minus the natural log of 1, but the natural log of 1 is 0. So the limit as b goes to infinity of the natural log of b is actually infinity, because this is what the graph of the natural log of x looks like. So as x goes to infinity, this is growing to infinity. So since we get an infinite limit, we would conclude that this diverges. All right, let's look at another one. So this is now the limit from 0 to infinity of e to the negative x. So once again, we'll take the limit as b goes to infinity of the integral from 0 to b of e to the negative x dx. So this is a pretty easy thing to anti-differentiate. So we're going to get the limit as b goes to infinity of negative e to the negative x from 0 to b. And here would be my recommendation whenever you end up with negative exponents. Before you plug any values in, rewrite the expression with positive exponents, because when you're doing limits, it's very important that you understand what's in a numerator versus what's in a denominator. So this is the limit as b goes to infinity of negative 1 over e to the x from 0 to b. Now let's plug in our bounds. And notice here, I cannot drop the limit until I'm done evaluating the limit. So this will be negative 1 over e to the b minus a negative 1 over e to the 0, which is just 1. So now you can see that this e to the b is in the denominator. And now as the denominator blows up, this whole term is going to go to 0. So the result of this limit is just 1, and that is a real number. So we would say that this integral converges. All right, let's look at another one. We want to go from 0 to infinity, right, of 1 over x squared plus 1. So this is the derivative of arctan, right? But just like before, we need to get rid of the bounds. So we'll say this is the limit as b goes to infinity from 0 to b of 1 over x squared plus 1 dx. So since the antiderivative of this is arctan, we need to evaluate the limit as b goes to infinity of arctan of x from 0 to b. So this will be the limit, right, as b goes to infinity of arctan of b minus arctan of 0, but arctan of 0 is just 0. So this is tricky because a lot of people don't remember what this graph looks like. But tangent of x, right, has vertical asymptotes at pi over 2 and negative pi over 2. That means the inverse graph has horizontal asymptotes at those two values. So this is pi over 2, this is negative pi over 2. Arctan of x, right, is the tangent graph, right, kind of flipped on its side. So if we look at this, we can see that as b goes to infinity, the graph is approaching the asymptote at pi over 2. So that means the answer to this limit is pi over 2, which is a real number, so this thing converges. If for some reason you needed the limit as b goes to negative infinity, well, at negative infinity, it's approaching negative pi over 2. So it's a good thing you should know what these graphs look like. All right, so the next one requires integration by parts to integrate. So this is why I wanted to look at this, because these different topics can actually be combined together. So this is going to be the limit, right, as b goes to infinity of the integral from 1 to b of 1 minus x e to the negative x dx. So this thing isn't really too bad, but we are going to have to do integration by parts. So it makes more sense to take the derivative of this because it's 1 and we can kill it than it does to try to take the derivative of this, which just will keep repeating over and over again. So we're going to let u be 1 minus x, and dv will be e to the negative x dx. So du is negative dx, and v is negative e to the negative x. So that means that the integral from 1 to b of 1 minus x e to the negative x dx is u times v, so negative e to the negative x times 1 minus x, right? And then we subtract this integral, right? But this times this is going to work out to be a positive, so you're going to have minus the integral of e to the negative x dx. So this is still can be directly integrated. So if we take this out one more step, well, the antiderivative of this is negative e to the negative x. So when we multiply by this negative 1, we get positive e to the negative x, right? And I would actually simplify this out a little bit one more step. We can factor out a negative e to the negative x. So that leaves me with 1 minus x minus 1, and this simplifies into negative x e to the negative x, and that's what we want to plug 1 to b in, right? Just like before I plug my bounds in, I would write this as negative x over e to the positive x, so we can distinguish between our numerator and denominator. And we're going to get negative b over e to the b minus 1 over e. Okay, and so it's a minus, that's why it changes to a positive. So this is what we want to take the limit of. And we can see here that this exponential term in the denominator is going to overtake this linear term in the numerator. So this whole term is going to go to 0. So the result of this limit is just 1 over e, which is in fact a real number. So this guy actually converges. So I want to look at one more example. How do you deal with the integral when you have to split it up into two pieces? Okay, so if you look at the structure of this, right, we can pick any c we want to split this up. So 0 is a really convenient number, right, and calculating e to the 0 is fine. and that shouldn't be a problem for us, right? But what I want to do here, right, first is we want to say, well, this is going to be equal to the limit from negative infinity to 0 of e to the x over 1 plus e to the 2x dx, plus we're going to pick up at 0 and go to positive infinity of e to the x over 1 plus e to the 2x dx. So I have to work with these separately. But since the stuff inside the integral is the same, and I have to integrate first anyway, we can actually do the integration and then come back and deal with the two bounds. So let's just deal with the indefinite integral first, all right? So I'm actually going to rewrite this a little bit and actually say this is e to the x over 1 plus e to the x, right, quantity squared. So believe it or not, this is now a version of some kind of arctan. And so if I do a u substitution here, I can say, well, let u be e to the x, du is e to the x dx. So now I can rewrite this integral and say, well, this is just 1 over 1 plus u squared du. Well, that is just arc tan of u. So if we go back to variable x, that's arc tan of e to the x. So that's the result of the limit. So now I have to deal with my bounds, okay? So the integral said, right, that we evaluate arc tan of x of e to the x. The first one was negative infinity to 0. So I'm going to evaluate that from a to 0. And then we're going to add that to arc tan of e to the x evaluated from 0 to b, okay? So we're going to take the limit of this as a goes to negative infinity. And see, this is the other reason we use this a-b notation, so you don't confuse the bounds of your limit, right? A should go to negative infinity because it was at the bottom of your integral, right? And b should go to positive infinity because it was at the top of your integral. So this is going to be arc tan of e to the 0, which is arc tan of 1, minus arc tan of a. Then we're going to add this to the limit as b goes to positive infinity of arc, oops, sorry, this isn't arc tan of a, this is arc tan of e to the a. This is going to be arc tan of e to the b minus, once again, arc tan of e to the 0, which is 1. So arc tan of 1, right? So now we have to evaluate these limits, and this is actually a little bit tricky. So I already showed you what the graph of arctan looks like on a previous page, so let's just revisit this for a second. So we know that if the stuff inside arctan is blowing up to positive infinity, right, it's going to go up this way. And if the stuff inside arctan is going to negative infinity, we're going to get negative pi over 2, right? So let's actually analyze what's happening here. So arctan of 1 is a constant number, and arctan of 1 is pi over 4. Because what arctan of 1 is actually saying is for what angle is tangent equal to 1. And tangent equals 1 when sine or cosine are the same, and that's 45 degrees, or pi over 4. Notice here this is arctan of e to the a, okay? But we're actually going to negative infinity. So the limit as a goes to negative infinity of e to the a is actually, because these values here are big negative, is actually the same thing as the limit as a goes to positive infinity of 1 over e to the a. Because these are going to be really big negative numbers, so it's actually going to shove e into the denominator. So you can see here that the limit of the stuff inside of here is actually going to 0. So what this is really saying is, what's arctan of 0? And arctan of 0 is in fact 0, right? For this guy, well, the arctan of e to the b, well, b is going to positive infinity. So this is blowing up and getting huge. So we're actually saying, what does arctan become when this value inside gets really, really big? And we saw on the graph, well, that happens when it approaches pi over 2, right? It just starts getting closer and closer to pi over 2. arctan of 1, well, that's just a known value again. That's just pi over 4. So now when we simplify this, we're going to get pi over 4 minus pi over 4. So those cancel. And so all we're left with is pi over 2. So this converges. So you want to be really careful when you're doing limits to negative infinity, especially if there's exponents involved. So a really cool trick you can do that I personally do all the time is the following. Whenever you're looking at a limit to negative infinity, of any function, okay, that is the same thing as taking the limit as x goes to positive infinity of f of negative x. So for example, if I want the limit as x goes to negative infinity of x cubed plus 2x plus 4 over x to the 4th plus 3x plus 5, right? I can say, well, this is the same thing as the limit as x goes to positive infinity, and I just plug in negative x values. So negative x cubed is negative x cubed minus 2x plus 4. When I plug a negative x into an even power, it remains positive, right? Minus 3x plus 5. So just like you would with any normal infinite limit, all you have to look at are, right, the highest powers of x. And so you would see that this guy equals -1. So when you're dealing with really, really big negative numbers, you have to account for that negative sign. And so I've always found that this is a really good, easy switch, right? So I'll show you one more. So if you say the limit as x goes to negative infinity, right, let's just do e to the x, right? We already said, well, that's the same thing as x going to positive infinity of e to the negative x, and e to the negative x is just 1 over e to the x. So if you looked at here, a lot of people would wrongly say the answer is negative infinity, and that's completely false, because the answer is actually 0, because that negative exponent is actually going to shove the term into the denominator. All right, well, I hope you guys find this helpful. If you have any questions, email me, and I'll see you guys next Monday for office hours.